So in this video we want to talk about the idea of molarity, which is the expression of concentration most frequently used in chemistry. So in general, concentration is really an expression of the quantity of a part per whole. So concentration, given the variable C, is the quantity of solute divided by the quantity of solvent or solution. So how much salt did you put in the water, or how much salt do you have in that solution that you made? That's the idea of concentration. Couple shorthand ideas for concentration. A lot of times you will see something like this, and the sodium chloride in brackets means concentration. It's an abbreviated way of saying concentration of sodium chloride. And in this case, the concentration is expressed in grams per liter. There are a lot of ways to express concentration. Like I said, the one that we are going to use most often is molarity. So let's take a look at molarity then. Molarity is defined as the number of moles of solute, so the number of moles of salt, per liter of solution. So liter, not any sort of volume, but it's got to be per liter. So molarity equals moles per liter. So this really winds up being an algebraic expression with three variables. In order to solve molarity, you've got to know moles and liters. In order to solve moles, you've got to know molarity and volume, and so forth. So this is not, you can incorporate these ideas into dimensional analysis, but if you're solving molarity on their own, you can think of it as an algebraic equation with three variables. So a couple of example problems you've got here. First example, how many grams of calcium chloride is necessary, there's bad English, how many grams of calcium chloride are necessary to make 500 milliliters of a 0.25 molar solution? All right, well, think about what you've got. You've got molarity is 0.25 molar. Your volume is 500 milliliters, not liters, so we've got to convert that into 0.5 liters. If you don't need to show me that conversion from milliliters to liters, that is one conversion that I'm okay with. What we don't know is moles. So if you find it useful to make a little list of variables off to the left, you're going to see in the units to come that we are going to use algebraic equations that can have as many as 8 variables. Sometimes it's nice to have the list of variables over to the left. Basically, what are we doing? We're starting off with this equation that we've already know, the molarity equals moles per liter. But what we want to solve for is moles. So let's manipulate this equation to isolate the variable. And this is one technique that I'm going to encourage you to learn, or I'm going to expect you to learn throughout the year. I want you to isolate the idea, isolate the variable that you don't know. Do that with the algebraic equation before you start plugging numbers in. All right, so now that I know that moles is equal to molarity times liters, I have 0.5 liters, and I have a molarity that is 0.25 moles per liter. So I just took these two numbers, but notice what I did. Instead of writing capital M, I expressed the units of molarity, moles per liter. That way you see liters cancel out, and I'm left with moles of calcium chloride. But I'm not done with the question, because the question was how many grams of calcium chloride. So one more step is to use the molar mass to get to grams. So notice that I took this idea, I took this algebraic equation, set it up to solve for moles, but kind of kept going as a dimensional analysis problem to get to grams. So I can do this all in one step. I don't have to solve this part first and then go to this part. Remember, every time you solve an answer, you're rounding that number, which makes your final answer more accurate. Anything you can do to keep the equation or to keep the math down. So if you can do it all in one equation, that's a really good technique to learn. All right, example number 2, what's the molarity if we take 62.91 grams of calcium chloride and make dissolve it in 250 milliliters of solution, or to make 250 milliliters of solution. So molarity is what we don't know. Volume, once again, 25 mils needs to become 0.25 liters. Mass is 62.91 grams. So we need molarity, so we have moles per liter is what we're shooting for. Well, at this point, if we put the mass over the volume, we have grams per liter. That's not quite molarity, but notice that I can very easily get to molarity by simply using my molar mass once again. So I can set the units that I have up to mimic an expression of concentration. Because remember, concentration is a quantity of solute divided by a quantity of solvent or solution. So down here, I have a quantity of solute divided by a quantity of solution in this case. So I have an expression of concentration in grams per liter, but I just want to convert it into moles per liter. So again, I can do this all in one-dimensional analysis step, and I wind up getting a concentration. Okay, that's idea number one. We're going to take some of the stuff you already know, including molarity now, and explore it in a little bit of a different way. So what if we wanted to know just the concentration of the chloride ion, for example? How would we go about figuring that out? So this idea is going to let you see that. Okay, so for example, we want to know what the individual ion concentrations are in potassium phosphate if we have a 0.2 molar solution of potassium phosphate. Okay, so we know that this is the concentration. We also need to consider what the ion ratios are. So you need to think about the dissociation equation. You don't actually have to write the dissociation equation, but you have to think, okay, if I put potassium phosphate in water, what's going to happen? 3 ions of potassium are going to get generated, and 1 ion of phosphate. Hey, I'm trying to focus that a little bit better. It seems a little blurry to me. 1 ion of phosphate, 3 ions of potassium. So I got 3 moles versus 1 mole. So my mole ratio is really 1 mole of potassium to 3 moles of phosphate to 1 mole of phosphate ion. So I can use this mole ratio to help me answer questions. If I know that the concentration overall is 0.2 molar, K3PO4, I can simply multiply by my mole ratio, 3 moles of potassium per 1 mole of potassium phosphate, to get my concentration of K3PO4. Same thing with the phosphate ion. It's a 1-to-1 ratio, so 0.2 gives me 0.2. Now, this idea can be applied to a bigger problem, but you could stop right here. We've answered the question, what are the potassium and phosphate ion concentrations in the 0.2 molar solution? We've answered that. So really what you're thinking about is what's the mole ratio? The original is 0.2. Since the ratio is 1 to 3, the concentration of potassium is going to be 3 times that, 0.6. It's 1-to-1, so the concentration of the original is going to be the same as the concentration of phosphate. So mathematically, this is how it works. But if given the situation, you don't actually have to necessarily show that work. Obviously, on a test or a quiz or a lab report or something, you're going to want to show that work. But if you're just working through something yourself, you can just think, what's my mole ratio? So that's idea number 2. So we've done straight up molarity, we've done ion concentration. You've got a couple problem sets to do for each of those. The last idea is on the back side, and that is when we do a dilution. Okay, so what I want you to think about, and I'm going to cover some stuff up first. When you do a dilution, what are you doing? You're adding water. Okay, so what I'm increasing the volume of the solution by adding water, which means I'm decreasing the concentration. I'm dividing by a bigger number, so molarity is going down. But what's not changing is the moles. The moles of solute that you had is not changing because all you're doing is adding water. You're just changing the total volume of the solution. You're not changing the amount of solute. So moles that you started with are going to equal moles afterwards, or moles 1 equals moles 2. Oftentimes we think about that 2 different situations. And I want you to remember that moles is equal to molarity times liters. We figured that out when we arranged the molarity equation. So if moles initial equals moles final, and moles is equal to molarity times liters, we can combine those 2 ideas and say the molarity times the volume initially is equal to the molarity times the volume in the end. So what's going to happen as my volume goes up, so these 2 are getting bigger, right? Volume's getting bigger from start to finish. What's happening to my molarity? My molarity is getting smaller. but they've got to multiply out to give me the same actual value. So this relationship can be described as M1V1 equals M2V2, or if we think about it generically, concentration times volume is equal to concentration times volume. Even though the concentration we typically use is molarity, please realize that it doesn't matter what the concentration is, this equation applies to it. So, like I said, the generic equation can be this one right here. Concentration times volume before equals concentration times volume after, because we're not changing the amount of solute. So let's take a look at a question. You've got 500 milliliters of a 0.5 molar, or you want to use 500 milliliters of a 0.5 molar solution. When you go to the stock room, you don't have 0.5 molar sulfuric acid, you have 2 molar. So what are you going to have to do in order to get that 500 mils? So we want to take some 2 molar and dilute it to 500 mils to get to 0.5 molar. So my starting concentration was 2 molar. How much of that starting volume do I need to use? So here's my C1 and V1. I know what my final numbers are supposed to be. Final numbers are supposed to be 0.5 molar and 500 milliliters. Now, what's nice in this is because these volumes are going to cancel out, as long as the units are the same, you don't have to change them. But just to be safe, if it makes you comfortable, please do change the volume to liters so you don't get yourself confused. But for those of you who are comfortable with it, you can leave them in milliliters. So what I'm going to do is I'm going to take this equation and rearrange it for my unknown. So V1 is equal to C2 times V2, and then I'm going to divide by C1 in both cases, equals C1. So I've isolated V1. So now I'm going to plug my numbers in. Once I isolated my variable, it's plugging and chugging. And I know some of you are going to resist me on isolating the variable before you plug the numbers in. I am going to deduct points if you don't isolate the variable first. I want you to learn that technique. It saves you a whole lot of time when you're dealing with larger equations. So C2, 0.5, V2, 0.5 milliliters, or 0.5 liters rather, or 500 mils, divided by the 2 molar. What do I get? I get a volume of 0.125 liters. So what does that mean? That means I have to use 125 milliliters of the 2 molar solution, and I'm going to have to add enough water to get it up to the target 500 mils. So 125 mils of the concentrated solution diluted to 500 mils means the difference between 500, my final, and 125, my starting, means I'm going to have to add 375 milliliters of water. So what would I do? I measure out my 125 milliliters in a large enough graduated cylinder, 500 mil graduated cylinder, and then I'd add it the rest of the way with water till I got to my 500 mils. Then you want to make sure, of course, this last idea, you thoroughly mix it to evenly distribute the solute throughout the larger volume. So always make sure that you mix the dilution. We are going to learn in our next class how to make a solution using this idea of molarity. So 3 ideas: dilutions, general molarity, and then ion concentration. So the problem sets that you're going to have to work on include all 3 of those. So come to class with a reasonable understanding and any questions that you might have. We'll hit on any confusions about these 3 ideas in class, and then we'll take some time and learn how to do these techniques, how to make a solution, and so on and so forth. All right. Have a good rest of your day.